All right. Good afternoon, and yes, welcome again for the communication signal processing seminar. We are at the regular time now, since we don't have people from faraway time zones. Just a reminder that next week we will have the seminars not on Thursday, but it's on Friday because Friday morning because Vivek Borkar is going to talk from India, and this would be too early in the morning for him. Anyway, so before I get started and welcome the speaker today, I just wanted to thank Shelley Felkamp and Catherine Goodwin for help arranging the seminars. Without their help, it would be very hard. And also I'd like to thank NCIS and SIPML for the support for getting the seminars going. So it's my pleasure to introduce the Srinivas Shakkottai, our speaker today. Srinivas received his PhD in 2007 from the EC department at University of Illinois. So I've known him from back then. And actually, we've been working together as well, so I know him fairly well. He was a postdoctoral scholar in the Management Science and Engineering department at Stanford University in 2007. And since then, since 2008, he's been at Texas A&M, where he's currently a professor of computer engineering in the EC department. His research interests are sort of veer in the networking to now reinforcement learning and stochastic analysis side. So in particular, his interests are in caching, content distribution, wireless networks, multi-agent learning, and game theory, cyber physical systems, as well as data collection and analytics. He serves as an associate editor for the IEEE ACM Transactions and Networking. He's a recipient of the DTRA, Defense Threat Reduction Agency Young Investigator Award in 2009, the NSF Career Award in 2012, as well as research awards from Cisco in 2008, Google in 2010. He received several awards at Texas A&M, including the Outstanding Professor Award in 2013, the Select Young Faculty Fellowship in 2014, and the Engineering Genesis Award in 2019. So Srinivas, go ahead, the floor is all yours.
Thank you, Vijay. Thank you all for being here. So yes, my name is Srinivas Shakkottai and I'm at Texas A&M University. The title of this talk, which is also the equivalent of the paper, which you can find on arXiv, is called Reinforcement Learning for Mean Field Games with Strategic Complementarities. We've got kind of three phrases here: reinforcement learning, mean field games, and strategic complementarities. I'll describe where they all fit in as the talk progresses. This is joint work with students Kiyeob Lee and Desik Rengarajan, as well as my colleague Dileep Kalathl, who is my colleague in the department. So let's get started. Now, before I get started with the actual technical content of this talk, I'll do a little bit of salesmanship here, which is what do I do? You know, actually, although I've been to Ann Arbor multiple times, I've never formally given a talk. I've visited multiple times, talked to Mingyan and various people, Vijay, Lei, but I've never actually given a talk. So let me just do a little bit of selling. So what do I do? Who am I? What do I do? So my background, as Vijay pointed out, is in kind of network optimization and control. So what I work in general is on large-scale networks and computing systems of various kinds, right? For example, one train of thought is on the communication information side. Specifically, we work on systems, for example, wireless networks, information dissemination. You know, you may have heard the word caching, P2P in the resume that Vijay read out. So we're basically moving bits around these networks. So on the wireless side, most of this is not on the wired networks. So we're trying to move things around wirelessly. And recently, I've also been doing some stuff on chip. So it's very, very tiny scale networks, scheduling of essentially tasks on chips and so on. And I do keep a foot, maybe even a foot and a half now, on the system side of things, which is actual instantiation. What you see here in this little diagram here is a software-defined radio, which allows full stack programming, so we can actually instantiate our algorithms. More recently, many of these problems which we look at are MDPs, Markov decision processes. So more recently, a good deal of what we've been doing with this is reinforcement learning, right? So effectively, the idea is that there is unknown sources of randomness, which we are trying to learn on the fly, basically, right? A good deal of the methodology that we use is stochastics, probabilistic modeling and analysis. So that's one kind of train of thought. Communication systems, information networks, effectively, which we are configuring in some manner using RL and other analytical techniques for analyzing their performance. The other train of thought, which is closer aligned to this talk, is on looking at network effects. Essentially, you have multiple agents, right? These might be things like smartphones, these might be human beings, algorithmic agents of various kinds, and they are somehow interacting with each other, creating equilibrium, right? So the question really is, of course, whether such equilibria even exist, how do you get to them, what is the nature of those equilibria, can we change them, these kinds of things. Specifically, the kind of networks I'm interested in, of course, communication. Electric energy has been something which I've been exploring for something like 5 or 6 years at this point, in which we actually built systems for trying to instantiate behavioral change. So we call this energy coupon. When I came last to Michigan, actually, I was trying to see, look for potential for effectively going public with this, in the sense that we wanted to try it out as an app. COVID kind of dampened a little bit of that, but we'll probably try to think about how we might want to instantiate some of these systems as an actual service in the future. So essentially what we were looking at, which we continue to be interested in, is so-called demand response. You provide incentives for behavioral change in which you reduce your energy usage at certain targeted times. That picture of that little cartoon is part of our app, which is called Grid Guru, which tells you how to kind of modify your behavior, also tells you what your house is up to in terms of energy usage, etc. Anyway, so, and of course, we are interested in transportation networks, where again, this multi-agent aspect comes in. So in general, the tools that we employ in this context are largely drawn from optimization and game theory. In particular, game theory naturally has this multi-agent part to it. So there are multiple agents with incentives which are trying to essentially take actions in some way beneficial to themselves. And we couple that whenever possible with large-scale data analytics, in which we try to model the behavior of these systems. Particularly, as I said, in the energy system, there is a good deal of data, both on the nature of the network, what is the network topology, etc., what are the demands placed on it, what are the market structures which apply on it, as well as essentially, once we have access to this little thingy called a smart meter, we know the behavior of the end user as well. And that was what Grid Guru was kind of combining together. Anyway, so essentially what this talk is about is coupling these two top things, which is essentially game theory with reinforcement learning. So this is going to be a pretty analytical talk, right? There is no systems component tied to it at the current time. But as I said, before going into the talk, I'll just give you a little bit more flavor of the type of problems I work on. So one major theme which I've dealt with for many years is on information networks, moving information around networks. Particularly, many of these are in collaboration actually with faculty from U Michigan, particularly Vijay, and now with Lee, earlier when he was at Iowa and Arizona, and now at Michigan as well. So some of these are collaborative works with them. And particularly the work on caching and content distribution, some of these ideas were developed in collaboration with Vijay. So essentially, we're looking at learning-based caching algorithms, where the thought process is that caching really is a means of learning an unknown distribution to make sure that when a request is sent in, what is requested is sitting there in the cache, right? Now, we've also on the system side been building kind of platforms whereby we can actually instantiate some of these algorithms. Specifically, we're building one for resilient information networks, wherein we can move algorithms to data in a distributed manner, right? So essentially, you think of these multiple agents, each of which is doing compute, which absorbs data and generates new data, and can move around a network in a resilient manner, in the sense that if nodes vanish, are taken out, this has a military context. If these nodes vanish for whatever reason, the state of the actual component, the algorithm which is operating on the data, can be seamlessly transferred elsewhere. So these are the kinds of things we've been doing. Now we work on, I mentioned electrical networks as a cyber-physical system. So we look at various network and cyber-physical systems. So reconfigurable wireless networks takes advantage of the fact today's networks are highly, highly programmable. Full stack programming is possible from layer 1 or even lower, beamforming, etc., all the way up to the application layer is software defined. So essentially, it provides a great platform for actually instantiating many of these RL algorithms. So what we've been doing here is on the analytical side, coming up with structured policies whereby we can configure these networks. And on the system side, actually instantiating it on a real network platform. Now, something which we've just started working on is teamed vehicular networks as well, in which we've got many of these little vehicles. They're called deep racers. We've got 10 of them, in which essentially the goal is to make them operate in a multi-agent manner, Essentially, it's a multi-agent RL problem with an actual application of obtaining kind of teamed behavior of those vehicles, right? Closer to this talk are games and multi-agent systems and markets. So we've been spending quite a lot of time over the years on pricing and coordination in networks. Particularly recently with Lei, we had a paper on mean field games in this context, right? As well as I mentioned, electric energy markets. Now, where do we actually build our systems and what is going on there? So this image on top is this Learning and Emerging Network Systems lab, which is the lab I co-direct along with Dileep Kalathl. So what we've got there is essentially a lot of hardware to play with. Big compute boxes. These are GPU-enabled Lambda Labs machines. Software-defined radios. Here's a software-defined radio sitting on top. These deep racer, the tiny little vehicles, etc. So we've got a lot of hardware to play with generally. And what is happening at A&M is basically where A&M, about 10 miles away from campus, is a former Air Force base, which was donated to A&M. And what we're doing there is we're building it out as an infrastructure, as a laboratory, basically, wherein we can do off-road vehicular experiments. In this case, these are tank trails out here. There's a quarry here, which can be submerged. These are the runways where we can do autonomous vehicle experiments. We own the airspace, so we can do UAV stuff there as well. And the cream, as it were, on this whole pie is this 5G network that we're building on top of it. So all these are base stations, of which these 3 are opened up for research, wherein I'm kind of designing a full stack kind of millimeter wave and sub-6 kind of outdoor environment, wherein we can do a whole bunch of experiments, mobility, beam steering, full duplex comms, etc., which is ongoing. So ideally within this year, we should have all this stuff up and running. So that's enough advertising. So let's come to the actual talk here today. This is on mean field games with strategic complementarities, right? This is a paper which has just been accepted, and so it's fresh off the press, so to speak. So what are we trying to do? First is on what is strategic complementarities, what is the motivation? So strategic complementarities basically has to do with a set of properties which provide structure to a game, wherein the marginal returns to increasing one strategy increases in the competitor strategies. In other words, the more that you do or the more that others do, the better it is for you to follow suit. So there is this alignment in strategies. There are many applications of this kind of thing, right? For example, in online social media, if you spend, if a lot of people spend a good deal of time on Facebook, then your doing so will also benefit you more because there's a lot more content, a lot more interactions, etc. So you get more gratification, so to speak. Online marketplaces have this characteristic in that if the online marketplace attracts many customers, that is, many people are doing a good job in that platform, then each driver has an incentive to do well because it would maximize their own rewards. You know, if drivers are doing well and Uber has a good reputation, then a driver doing well on Uber is likely to be rewarded well, right? As opposed to a platform which people think worse off or badly off, in which case doing well on that platform is not going to reward you well. So in other words, there is this alignment here in everyone doing well. Another thing which is kind of the running example for this particular talk follows from COVID, which is if lots of people are following social distancing, mask wearing, things like that, then everybody has an incentive to do so because it's effective, right? Specifically, we know for a fact that if a large fraction of the population is indeed washing their hands and wearing masks, then it is valuable for you to do so because it improves your health outcome as well as, in turn, it helps everyone else, but really it helps your own outcome because there is alignment in terms of the value of what you do with respect to the value of the others doing it. Essentially, this is what we're saying. Strong actions of the others means more benefit from your doing the same, and therefore that elicits stronger actions from you. So there's a herding mentality in these games. Why strategic complementarities? Why are we looking at this class of games? In general, the analysis of generic strategic games, or in this case, stochastic games, is tricky without additional structure. So in other words, what we're looking for in general is structured games of some kind. This is one way of providing structure. You may have heard the words, for example, potential games, for example, zero-sum games, etc. So this is a particular class of games which provide structure, which has some interesting applications, but exploiting that structure enables us to get interesting analytical results. So we'll come back to this idea of strategic complementarities. Before we go into what is the nature of equilibrium and so on that we're interested in, I just want to provide a very basic Bayes-Nash game or a Bayesian game and just bring you up to speed, so to speak. Probably most of you know this quite well. on what is the nature of a Nash equilibrium here and what is the nature in the general stochastic game that I'm going to come to. So in general, a Bayesian game has a state space, an action space for each the players, potentially a probability distribution from which states are drawn. So these states are sometimes called types in the Bayesian game. And of course, a reward structure. So each user has some reward, right? So, and I is the index of the reward of the user, there are n of them here. So essentially the point I'm trying to make here is the nature of a Nash equilibrium here is the following. So effectively each user has a state which is drawn from that distribution P. So there are in this case three agents or three users shown. Each of them has some state which is drawn. Everybody knows that distribution. Typically the users do not know the states or types of the other agents. Now, based on this belief, this distribution from which it is drawn and your own state or your own type, each user can potentially, if there is an assumed mixed strategy, that is the probability distribution whereby each of the other agents is playing. Notice these are of course independent of each other. So the first agent assumes that player 2 and player 3 are playing mu2 and mu3 respectively, and it comes up with the best response. It needs to compute its value. This is simply a one step. There is no time here. So there's just one step, and it comes up with a mu1 in response to it. Mu2 considers mu1 and mu3 comes up, player 2 comes up with mu2. Player 3 comes up with mu3, assuming mu1 and mu2. Now, a fixed point is basically in the basically a Bayes-Nash equilibrium, in which effectively you start with a belief mu1, mu2, mu3, and the best response comes out to be mu1, mu2, mu3 itself. So in other words, this is a optimality condition. The resultant is basically optimal from the perspective of your belief. Great. How will we generalize this? The generalization of this is called a stochastic game, right? So this does have time. It is going to be played over and over again. The most general stochastic game. So there are variants on the theme. So the question really is, I had this idea of state up here. Now, you could say, for example, that you could repeat this game in which your state is drawn independently at every time, right? That is one option. There you notice your actions have nothing to do with the state. The state is just drawn every time. The other possibility is the state evolves, but still your actions have no impact on the state. But the most general version is that this state is indeed impacted by the actions, and therefore this evolution of the state is actually according to a Markov process. And therefore, what you have here is a Markov decision process with multiple players. So effectively then, a stochastic game in its all its glory, its generality, is again you have states, actions, this transition kernel, rewards, and a discount factor here. So effectively what is going on here is we have the state space, action space, n players, and discount factor, right? This is pretty standard. Now the reward here, you notice each player's reward depends on basically the entire state and the entire action. So this state, of course, is the state of all the n agents. The action is the actions played by all the n agents. Now this is of course tricky because it depends on everybody's states and actions. Furthermore, this is where it gets really hard. The kernel, the transition kernel, where the state is going to go, the next step, depends on everybody's state and everybody's action. So in other words, the next state S dash is going to be distributed according to probability where the conditioning is on the entire state and entire action, right? Now, these stochastic games typically admit a stationary equilibrium. However, they're really hard to analyze or to attain this equilibrium because as the number of players increases, you notice the information set of these players is getting bigger and bigger and bigger. So you have to basically account for the beliefs of these players as they evolve in time. So essentially, you're going to have to track the exact behavior of all players. Now, if you've got a fairly large game in which there are many, many players, essentially, this is neither feasible nor is it practical in the sense that you would expect that no agent, no real human being or other algorithmic agent has so much compute power and memory to actually find the optimal solution here. It is under the circumstance that the mean field regime comes into play. Mean field regime, if you will, is an asymptotic simplification of the system, which, and Professor Ying has several nice results on convergence in this context, on as to the rate of convergence in the asymptote. The mean field regime is the following. So basically what you do is you consider the empirical distribution of state of these players and call it the mean field. So what's going on here? So basically we're saying, this is of course, we're looking at a tabular regime in which we have finite states, finite actions. So in other words, we tabulate the number of players in each state. So I is the indicator function. So we are just saying if a particular player is in a particular state SI, then you get a 1 here, else you get a 0. So we're just counting the number of players in each state, dividing by the total number of players. So you basically get an empirical distribution of players in that state. So that Z, therefore, is essentially the empirical distribution. It ignores the identity of the other players. So in other words, I know myself, I know my state, I know what I'm going to do because I can compute, but I just account for the distribution of the other players. So how does this work? So it's an approximation of the stochastic game. So you notice this looks very similar: states, actions, transition kernel, reward, and discount factor. Yeah. However, this reward function now is basically is a function of basically the state, my action, and the mean field. It is not explicitly a function of the other A's and the other S's. It only depends on the Z, my own state, and my own S. And as I said, more importantly, the transition kernel also is like that, in that the transition probability depends on my state, my action, that is the ith, the mean field, but not explicitly on the other SIs or AIs, right? Therefore, this is the distribution of the next state. Okay, so this is basically, incidentally, this is called a state coupled mean field. If you were to put the action distribution here, you would have the action coupled mean field. So anyway, this is a state coupled mean field or the transition curve. Now, this approximation, of course,
and the Srinivas, the assumption is that you know the distribution.
We will see in the learning regime. Hold the thought, I guess. In the computation aspect, you know P, you know Z, right? But in the learning part,
you know Z. I mean, in this assumption is you know Z as well.
Here we, yeah, exactly. Okay. In other words, if you know the kernel, indeed you know Z. Yes, for sure, right? So yes, and that's where the nature of the equilibrium will also come in, because Z has to be consistent with what you're doing. This approximation becomes more accurate, and what we're looking at is the state coupled mean field games, and of course homogeneous pairs, so they all look similar. And so what we're looking at is something like this, right? So if you try to run this system over time, what would happen? You have this existing mean field state distribution. This is the ZK. This is what Vijay pointed out. Let's say it's available to you. There is a strategy profile that was being played last time, right? It's the one which is being computed from what has happened in the past, specifically the ZK minus 1 and so on. Now, given these two, you've got a strategy profile and you've got ZK. Then essentially what you can do is effectively compute what is the value function. So if you know the transition kernel, you can actually do value iteration or Q value iteration in this case, so as to learn what is the optimal policy for a mu k minus 1 ZK. You can try playing that next time. And of course, at this time, you have to do something, that is A, you're taking an action. And when you took that action, of course, you have a transition. So essentially, the transition is going to be based on S, A, and Z, you're going to have a transition. So what could happen here is, if you want to try to understand how this system evolves with time, what you do is these little loops indicate that in order for you to determine this best response mu k, you need to run this Q value iteration to infinity. You need to run this over and over again with knowledge of the transition kernel to find out the optimal thing. And given the policy that you're using, this mu k minus 1 and the transition kernel, you have to effectively, you can conduct a thought experiment, or you can run this for a very long time to obtain stationarity here. So this would be the stationary distribution that corresponds to a particular policy and of course corresponds to a particular belief. So basically this is the stationary distribution that follows from this kernel. So you could do that. You could basically—
Hey, Srinivas?
Go ahead. Yeah.
Yeah, can I ask a question?
Please,
so why are the mu k minus 1 the strategy profiles needed? Can the agent just based on ZK to find out what will be the best policy?
So the mu k actually determines, well, let's see. So the transition kernel doesn't depend on the mu k, but this action is going to depend on the mu k. The action that you take.
You mean mu k minus 1. Mu k minus 1.
Yeah, this action depends on mu k minus 1.
So you assume all the other agents are using the policy mu k minus 1,
correct,
and I want to figure out my, okay.
Yeah, mu k minus 1 is the policy of all the agents. There's no agent index here, but yeah, everybody's doing this.
Okay.
So this is one way of potentially computing the equilibrium. Possibly, if this converges, it might be a mean field equilibrium, right? So I want you to keep this diagram in mind, because this whole talk is going to revolve around what you need to do here and what you need to do here, right? In this particular example, I'm basically saying that given this belief and given the kernel, you run the value iteration to completion. In other words, you find the best response. That's what is going to be mu k next time. And given again the kernel, you're going to run this to stationarity, which is what is going to be the next mean field, right? So if you do this, you will get a sequence of best response mean fields, which may converge. We don't know, but it might. And the point is, each of these steps, there's going to be a mapping for, assuming that you have found a mu star, the optimal mu for a particular z, there will be a map between the current mean field distribution to the next mean field distribution. So each time, as it were, this the existing mean field distribution goes through this whole process and turns into the next one. And then it goes through the whole process and turns into the next one, etc. Maybe it will converge, maybe it won't. Does a fixed point even exist is one question, right? So effectively, what is the nature of a mean field equilibrium here? For any z, any belief distribution, a player's objective, a single player's objective, is to find a policy mu star that maximizes his total discounted reward. So this is the reward at any time with the z there, discounting going on here, etc. Right? Now, if we run value iteration to completion, it will converge to some unique solution. Now, how does the state evolve? So now we are given this belief and this policy. So we are given this mean field and the strategy. Mean field evolves according to this discrete time McKean-Vlasov equation, which is the following. And this answers Leigh's question as to where mu comes in. So the z evolves in the following fashion. So z evolves as a function of the current z, z dash is a function of the current z and the policy or the strategy employed in the following manner. So basically that z dash looks like the following. So first of all, you take actions according to a certain policy with a certain probability. That is the strategy here. If you did that, you would have a certain transition probability, and you must have been in a certain state S, and the probability of being there is Zs. So in other words, the way the Z evolves for a given policy, for a given belief, which is the state distribution, the empirical state distribution, is in this following manner, right? And this is called the McKean-Vlasov equation. This is the one-step McKean-Vlasov equation. So each time you run it, give me a Z, give me a mu, I'll get a new Z dash out of it. Okay? Now, the mean field equilibrium is a pair mu star Z star. It's a policy and a mean field that satisfies both a so-called optimality condition and a consistency condition. The optimality has to do with the rationality of the agents, which is that what you do, the mu star, the policy that you employ must be an argmax policy for the given mean field belief. So for a given Z star, I'm trying to maximize my payoff, each agent of course, is trying to maximize their payoff, and that the output of that should be mu star. So it must be optimal for the given belief. The second aspect to it is basically consistency, which is basically that if you give me the Z star and the mu star and run it through the McKean-Vlasov equation, you should get the Z star back as the output, right? So essentially going back to this diagram, effectively what we need for an equilibrium is this Z should be fixed at Z star and this mu should be fixed at mu star. Whereas I said this mu star is a best response to Z star, and the Z star is an output of the McKean-Vlasov equation, which essentially is mapping the Z back to the Z, the next Z. So in other words, the Z star mu star should give Z star there, and this mu star should give back the mu star there. Right? That's essentially a mean field equilibrium.
Hey, Srinivas, so just want to follow up on the question I asked. So here, if you look at the optimality condition, that seems to need this mu k minus 1. You right. Optimize based on Z, right? Not
correct. Yeah. That is true. The best response doesn't need it, but the transition does.
The transition, right? Transition, but it's not like some decision an agent need to make. The transition is like the system's transition.
Correct. This, right. But the mu is in there. That's what I'm trying to
say. Yeah, of course.
That's all I'm trying to say. Yeah, you're right. Yeah. So yeah, absolutely. Now, so one thing that we want to introduce into this is this idea of randomness, and essentially, typically we don't think of an additional randomness introduced into the system, but for the learning environment, we would like to have an exploration component to this. And the point is, how do you introduce a concept of exploration? How we introduce it in this context is through a fairly old idea from Selten on so-called Trembling-hand-Perfection. So Trembling-hand-Perfection has to do with this idea that it's a way of refining Nash equilibrium. The idea is that you add a certain randomness to your strategy, and that randomness you cannot control. It's like your hand shakes. You wanted to do something, but you wound up doing something else. So players may choose unintended strategies with a small probability. So in other words, you forgot your mask or you didn't wash your hands, etc. You did something else. And so essentially, the point is we're adding epsilon randomness to the off equilibrium plane. So you find your argmax thing and you add this epsilon randomness. However, there is a big difference between Trembling-hand policy and epsilon greedy. In epsilon greedy, you compute the optimal policy and just arbitrarily add this randomization. So it might result in arbitrary loss of value, right? So in other words, if you think of epsilon greedy, it is not rational in the sense, if you add that epsilon, you might get very different payoffs potentially from what you expected, right? Under the Trembling-hand policy, the epsilon randomness is accounted for in the value function, right? So when you look at the expectation under the epsilon greedy policy, you maximize under the assumption that you are going to play epsilon Trembling-hand policies in the first place. This will change the nature of the Q function, right? It becomes a more generalized version of Q value iteration, which is what I'll describe in a second. So anyway, so what is a Trembling-hand-perfect mean field equilibrium then? So we're basically looking at this generalization to dynamic games of this Trembling-hand idea. So effectively then, policies now are going to be mixed by definition. Our policy space are going to be, the set of policies allowed to us, which goes from state to the kind of actions available to us, are the epsilon randomized policies. So in other words, these epsilon randomized policies are going to be those which one action will have most of the mass. You know, there's a mu SA. So a particular action in my policy will have much of the mass, but every other possible action, like, you know, A not equal to AS, will have basically some epsilon mass, you know, in terms of the cardinality of the leftover actions. So effectively what we're saying here is that I calculate the argmax itself is calculated assuming that the policy is going to contain an epsilon randomness. So in our Trembling-hand-perfect mean field equilibrium, it's much the same definition. It needs an optimality condition and a consistency condition. However, this V here is basically accounts for the randomness in the system. And in order to do that, we'll need a generalized value iteration so that we can actually compute. Okay, so that's this is the same to yeah. Go ahead.
So Srinivas, a quick question here. Trembling-hand-perfect equilibrium, I mean, that is, I mean, in the dynamic game, it's only for finite games, though, right? Because you need a finite. Basically, you have policies.
Mm-hmm.
You can think of pure strategies, which you basically then you're going to choose any of those with at a minimum probability, right? That's what you're doing. And
so this is finite state, finite action. Yes, this is tabular.
But also finite time horizon. I think you need that as well.
Not really. So you're
for Trembling-hand, you need a finite game. You cannot. I mean, because you have. So the idea in some sense is at time zero, you can play. You think of playing the entire strategies, right? So you only have a finite number of strategies. If your time index is going to infinity, then you have an infinite number of strategies.
But we're fixing the epsilon. So in other words, we're basically using it in the manner of essentially randomized policies, essentially totally mixed strategies, basically. That you never play a pure strategy, you always may play only a totally mixed strategy.
No, that's fine, but it's the question is, you're doing, you're sort of converting it into a behavioral strategy, which is totally mixed in some sense.
Exactly.
That's what you're doing, okay.
Right. And the one thing which we do, however, or in addition, or because of this, is because that we have essentially a strategically consistent strategy. This randomness that we are added is included in the value function as opposed to being imposed afterwards. That's the point I'm trying to make. So the difference, as I said, is first finding the argmax and then adding epsilon randomness is not strategically consistent because the value function doesn't account for that randomness. Whereas what we're doing here is that because we add the epsilon into the strategy itself, we have a strategically consistent strategy in that the value of the policy is indeed the expectation accounting for the epsilon. That's what I'm trying to say.
Hey, Srinivas, I have a follow-up question. So with this epsilon randomized policy, can I further do randomization on my actions? Like with one probability, 1 minus epsilon, I have to take a deterministic action or can take an action from a set of actions?
So here we're looking at a single action because it's a scalar and You're basically saying, how about randomizing across multiple actions here, right?
If there's tie, can I break a tie?
Tie, you can do it. Yes,
okay.
That's perfectly easy.
Okay.
Yeah. So one more thing before we proceed, which is the nature of the mean field game with strategic complementarities. So I mentioned that mean field games with strategic complementarities have this alignment, right, across the different players' incentives. The way this is formally defined is, of course, we have this, the stationary mean field game. And we say that it has strategic complementarities. If, first of all, the reward function is non-decreasing in state, right? And is supermodular in SA and has increasing differences in SA and the mean field. The way to think about this, because we're looking at discrete action space, right? We're looking at effectively and discrete state, there's finite state, finite action. We're looking at things which live on lattices, right? So we're basically trying to say that we've got a state action and of course a mean field distribution as part of our information set. And the reward function being supermodular in SA approximately is that it is convex, and increasing differences together with supermodularity in SAZ essentially means that it's convex increasing effectively in your in the state action and Z. Now, the other thing which is part of the supermodular, strategic complementarity structure is that the transition kernel is stochastically supermodular in SA. So where basically we're defining the stochastic supermodularity in terms of dominance. Effectively, this is the cumulative distribution. So the first order stochastic dominance is basically the cumulative distribution of the one is greater than the cumulative distribution of the other. Or if you take the expectation with any bounded continuous function, the expectation of the one is bigger than the other, right? So effectively then,
monotonic.
Sorry?
For monotonic functions, right? Yeah.
Oh, sorry, about monotonic.
Increasing function.
Yeah, increasing function, sorry. Here, of course, this is only showing the CDFs, of course. But yeah, yes. And furthermore, we require that the P has increasing differences in SAZ and non-decreasing stochastically in each of SA and Z. Now, these seem fairly strong, but it turns out that essentially the structure does hold, particularly what is the most important thing is the supermodular structure of the reward function. That gives you the alignment you're looking for. Basically, if you, the kind of visualization or feel for it is, if you've got convex increasing rewards with state, if everybody is at a high state, it essentially your playing actions, larger actions increases your reward more and more because you're already high up, and the increasing differences property means that you have higher rewards for playing those actions when everyone else is already in a higher state.
So that's kind of like induced kind of herding kind of behavior in the system.
Exactly. So you'll get, essentially the idea is you'll get this monotone sequence of these Z's which result from this. They'll kind of herd together as they move forward. Now, the first thing we need before we can talk about learning and other things is the existence of this the Trembling-Hand mean field equilibrium. Essentially the point is that if we have this stationary mean field game, the question is, does there exist a Trembling-Hand mean field equilibrium? And the way we do it is we have fixed point theorem. In this case, Tarski is because we are looking at lattices, finite state, finite action. So we basically want to look for a map from L to L, from the domain back to itself as a non-decreasing function. Then the set of fixed points is a non-empty complete lattice. So what we're really showing is trying to look at the nature of that map which goes from Z back to Z. Remember, I said that you have that belief Z, and you had that mu, which was the best response to that Z. The question is, if you played that, would there be the resultant Z? Is there a fixed point such that that map has a, does that map have a fixed point, which is exactly what we're looking at. That map, which I called epsilon at the time, is the same as the T here. So effectively, the way we show it is, the first is to show that the V star, the value function, is non-decreasing and has increasing differences. And resultantly from that, the strategy that you play is stochastically non-decreasing. That is step one. The Makin-Blasov update, which is the one-step update, it also turns out it's also stochastically non-decreasing in Z mu, provided that mu is stochastically non-decreasing in S, which is true there. So this is what is the herding thing. So effectively, you basically, the next Z, the sequence of Z's are going to be monotone basically. And then basically, if we have this epsilon, which is this map from the strategy space back to the strategy space, right? where this epsilon z is a McCain-Blasso equation with the best response sitting here. Then essentially, we basically use these first two, the step 1 and 2, to essentially validate the conditions of Tarski's theorem, and we can get that this map is stochastically non-decreasing, and then we have our fixed point. Okay, so first thing was the mean field exists. Now, what we do next is try to compute the mean field, and then we try to learn the mean field. So how do we try to compute this mean field? So what we have thus far is basically a framework of what is our mean field game and how we have Trembling-hand mean field equilibrium. We have the existence of the T-MFE for our problem for strategic complementarities. Now the question is, how do we compute it? Now the problem is, in general, there is no general algorithm for finding mean field equilibria. So because the McCain-Blasso equation is nonlinear, and even if it is unique, it's not clear. The diagram I wrote, the Z mu diagram, it's not clear if it will actually converge to anything. It turns out that this mean field games with strategic complementarities is an exception. And there's a paper by Adlaka and Johari which looked at this for the computational angle. And they actually used an algorithm very similar to what I had shown there. In other words, you compute the best response, then using that best response, go to the stationary distribution, use the stationary distribution to compute the next best response, etc., etc. So what we did was generalize this to a slightly different variant. First thing, of course, is we need Q value iteration accounting for the epsilon, which is what is going on here. So essentially, when we look at, we basically define this pi EQ, which is essentially saying that if the action is the argmax, we impose a 1 minus epsilon mass on it. Else we impose for all other actions, we give them equal mass. And then we can basically define this function, which is kind of this weighted Q function. And so we do Q value iteration with the weighted, the GQ instead of the regular Q, right? We can show this is actually an existing result for very general kind of Gs. There's a result which by Sepsavari and Lipton, in which they show that it actually converges to a generalized Q function. So in our case, we call it TQ value iteration. So basically the point is this is going to converge to an appropriate trembling hand version of Q function. Therefore, now what do we have? We basically are in the position where we can try computation in which we do TQ value iteration here, run it to completion. If we use the Adlaka-Johari algorithm, we would run this to stationarity as well. But we say that is going to be complicated. Our goal actually ultimately is to have only one step here and one step there, because it's impossible to actually run this to completion. You can only get an approximation in any case. And similarly, it's impossible to actually run this to stationarity because ultimately it will asymptotically converge, but you can't actually do it. So we thought, okay, let's assume that you are capable of running this to completion. That is, you can find the best response, but we only do one step McCain-Blasso equation. What do we get then? We get an algorithm of this form. This is a pure computation algorithm. You know the P, you know the kernel, the Z is given to you. Let's just try computing. So we initialize the mean field. And then what we do is we find the optimal TQ value function. That is, we run it to completion, find the trembling hand strategy, of course, and compute the next mean field in a one-step manner, right? We just run the McCain-Blasso equation once. We can show that this converges to the mean field equilibrium. It's similar to the thing where the proof of theorem 1, where this monotonicity property, that is the Z's have this, stochastically they are monotone because of this game structure. So essentially what happens is, we are going to get the sequence of mean fields, and this limit point will be a T-MFE. And in this particular case, what we have is a sequence of mean field ZK, which is a monotone sequence. And so there exists this, by a certain number of iterations, you will be epsilon close to the ultimate Z star. So we use this to find a sample complexity result. So we're basically saying that there exists some K at which the ZK, if you were to do computation, is arbitrarily close to Z star. And so basically, if you were to run whatever algorithm we are going to show you next, up till that K0, we basically will get arbitrarily close to the approximate answer. In other words, in a pack sense. Okay, so I have enough time to tell you about the two learning algorithms that we have. So where are we right now? We basically had a computation algorithm for the T-MFE, which follows this idea of Z mu. And we showed that it converges to a T-MFE. However, it needs the kernel. It requires the model. So in all the RL literature, the knowledge of the transition kernel is called the model. So we need it for TQ value iteration, in that in order to compute the value function, we need the kernel. In the McKean-Blasov equation, we need it because in order to find out the next mean field, you again need the transition kernel. Question is, can we do away with it, right? So what we would like to do is try to understand what happens when this is unknown. That is, we don't know the P. Now, one approach which is often done is a simulator-based system, wherein you assume that you may not have the P, but the P exists in a black box simulator. It's somewhere available to you. For example, if you're playing an Atari game or something, Super Mario or something, although you don't know the rules and structure of the Super Mario game, the game is available to you. You can play it kind of in a thought experiment, so to speak. So you have a simulator. So supposing you had a simulator, you could interact with that simulator as many times as you feel like, and that is one approach. We want to go away from that approach, but that is a possibility. So in other words, in RL, typically, there's a simulator that these agents could interact with. So you can freeze reality, as it were, put it into the simulator, interact with the simulator, come up with your best response, play it in the real world, freeze reality, put it into the simulator, interact with it, come back, and so on. So essentially, if you had such a simulator, you could actually collect samples by employing any particular strategy in the simulator, right? Then you could do Q-learning, right? Because you can continually just, essentially what I'm saying is, the mu k and the zk are sitting in the simulator. Only you as a single agent, you basically obtain samples from the simulator in order to learn your Q function. We'll do this next without the simulator access. But if you did have a simulator, you'd get something like this, which is, again, you have the zk and the mu k. You put them both into your simulator and run the simulator for a while. You can't run it to completion. The simulator only will run for so long after all. So you'll get an approximate Q function. Then you take the one step in the real world, the one step transition, and then you go on, right? So this model-free learning algorithm, if we have basically we define this TQ learning algorithm for this in the following manner. This is exactly the traditional Q learning algorithm, except that we've put in this G here, this generalized Q value iteration, the G for the generalized Q value iteration. And we can basically show that asymptotically the thing will converge, right? So that's the G which I want to point out. So this algorithm looks very similar to what we had earlier, except that we, of course, initialize the Z0 as we did, initialize the Q and the S. Then what do we do? So basically, we are going to take an action in the real world. Then here is where we are going to use the simulator, which is we update this Q using TQ learning in the simulator. So we do that, get the new strategy, and again, employ it in the real world, right? That's what's going to happen. So essentially, this stuff here, there is basically a part which is in the real world, and there's the part what I just showed you was the simulator, and then there is the actual employment in the real world. Okay, so that's on the model-free learning with simulator. Now we can come up with the sample complexity result. I just want to point out one thing with the sample complexity result. The question is, how close are you to the mean field equilibrium after how many steps? I want to just point out that traditionally you have in most RL algorithms, the sample complexity is in terms of the state and the action. Here you notice it's logarithmic in the state and action, which looks nice. However, I want to point out there is a factor L here, which is basically the covering time of our system. So basically it could be that for large disconnected Markov chains, although it's not bad in terms of the state and the actions, this L itself could be S times A. It could be very large. But nevertheless, it looks promising. And it's a candidate for employment if you had a simulator, right? Now, the last thing I want to talk about is learning from the real world. So where are we again? We assumed that if we had a simulator, we could stick in the current Z and the mu into the simulator and essentially learn our Q functions in the simulator. But you notice, rather than each agent employing a simulator, we actually have essentially asymptotically large number of agents. Can't we use them to learn? So rather than learning in time in a simulator, can I learn over agents in the real world? So essentially the question is, what are these issues when we learn without such simulator access? And can this algorithm be robust? In other words, will it actually converge to this mean field equilibrium? So effectively, a model-free RL approach is of this kind. So essentially, we generate this trajectory of samples to obtain this Q star. And then basically that Z mu characterizes the McKean-Blasov equation. So what we would like to do is we replace this collecting of samples from simulators to collecting it from agents. However, there's one issue, and that issue is visible in this. The issue is the following. I employ a certain strategy profile today, but by employing the strategy profile today, I change the state of the system itself. So therefore, what I learned across these multiple agents about the transition kernel today no longer applies tomorrow, because the transition kernel itself has changed by virtue of the fact that I changed the state. However, it turns out that this monotonicity property of the strategic complementarities means we are actually robust to that mismatch, which is why we're writing mu k minus 1 here and mu zk here. So although these are mismatched in the sense that this mu k actually corresponds to zk, it is the best response for the learning that was obtained with zk, and that's what you're going to employ on zk plus 1. But in spite of this mismatch, it still works. So the algorithm, I'll show you the algorithm diagram in the description in just a second, is basically what we were hoping for. We just do one step here and one step there. What are these one steps? So you take this policy of yours. Each agent employs one step of the policy. You collect all the reward functions and send it to essentially a platform, Facebook or whoever it is, a government agency, Uber, whatever it might be. That platform then takes all these samples and computes the next, basically, best response function. And then you employ that best response and provide the samples back. So effectively, rather than each person doing a simulator, you're effectively gathering a large number of samples in the real world. So that gives you an approximation of the Q function. And of course, you run the one-step mean field. So the algorithm then is essentially this, in which you basically observe the current state and take the action drawn according to mu k minus 1. Again, I want to point out the k minus 1. You get the reward and observe the next state. Send this stuff to a memory buffer. This state, action, reward, sk plus 1. This memory buffer is retained in the cloud somewhere. So you just send it off there. And what does the memory buffer do? It does Q-learning, essentially, over all the points in the memory buffer. Now, there might be some subtlety here in that are they all equally represented, etc. And in order to do that, we basically assume the following regarding these agents. So in general, for many mean field problems, the idea is, one way to obtain the independence needed for the mean field assumption is that agents come, agents spend a certain time, and agents leave. And when the agents leave, they are replaced by an agent drawn from some arbitrary distribution, right? So effectively, what this means is these agents who are newly coming in are drawn from some distribution. We assume that distribution has a support over the whole state space. So what this means is these agents who are sampling the world for us, right? There are agents who are in all the states so that they will sample the world, as it were, from every single state, right? That way, essentially, you have an arbitrarily high accuracy with an arbitrarily large number of agents. So in other words, as your number of agents increases more and more, your approximation to the Q function using the world as your simulator becomes larger, more and more accurate. Right?
Hi, Srinivas.
Please.
Since you are using the epsilon randomness already in the policy, will that automatically guarantee, like at each time, like you have a non-trivial probability, like all the agents will be in some
state? That is the point. That is indeed the point.
Okay.
Exactly. Because I need samples of all state action pairs, really, right? So effectively, the epsilon randomness guarantees that we have sufficient samples of all the state action pairs that as the number of agents becomes larger and larger, this Q function is arbitrarily accurate.
So you don't need like the agents join and leave the system, right?
The agents joining and leaving the system is because I need them all in all the states, right? It's not just actions.
Yeah, all the state, because you're taking random actions that also guarantee their non-trivial probability they'll be in all states, right?
Okay. So that is true, but okay. In terms of the proof, what we do is
that need not be true though.
Need
right?
not
that
be
depends
true.
on what your transition kernel is, right? So
exactly. Supposing I had it might well be true, but it certainly.
I think it's true because every action is taken with a non-zero probability.
But will you
so
get
if the Markov chain is it's irreducible, then you can get any state.
Can you show that every state has a essentially non-zero probability?
I mean, it's finite state. It is finite state, right?
It is finite state.
Yeah.
Is it possible that the kernel at some point will take all the mass to a smaller subset?
Could be. Yeah, I need to think about that. yeah.
That's the fear.
That can happen. I mean, you need what this identifiability thing to hold. It may or may not hold in this context.
So yeah, this was something which we went back and forth on a little bit. But ultimately, we decided that any case for the mean field assumption to hold, we need the correlation decay. And for the correlation decay to hold, this idea of agents entering and leaving is the kind of most easiest way to make it hold. In other words, geometric lifetime of the agents. And if you get that, then you get this representation of the whole state space for free, because that initial distribution, if it is basically occupied, if it supported the whole state space, then you will get it for free. So then the epsilon randomness will give you all actions, and the regeneration of these agents will give you all the states. That's the point. So then this thing will actually make sense. This memory buffer will have everything you want. That's the point I'm making. Any other comments on that?
Cool. No, I'm good. But we can talk offline to see whether that epsilon randomness can guarantee you can visit.
Guarantee the entire.
It may not guarantee it actually. You may need.
We are explicitly making it hold. Basically.
Yeah, we can also discuss.
Okay. Yeah, sure. No problem.
We could talk after this talk is over. For example, nothing much else I have to add. We do numerical experiments and everything works as expected. Particularly, we used this COVID example as our thing where health. How healthy are you is your state space. Action space is basically actions you could take. These are scalar actions, and essentially we wanted to show that effectively the GMBL is the generative model-based learning, in which basically we sample the system till we find the kernel, then we just solve it, right? And the online and TMFQ learning are the two variants of the learning algorithms. They all converge to what we expect they should. And essentially, we're looking here at the CDFs of online learning for various different parameters of how infectious the thing is. It converges over time. What was most interesting to us was how does this change with the number of agents? And here is where the mean field or lack thereof comes into play. And so again, this is the number of samples you use effectively for the Q learning. Again, this goes back to Lei and Vijay's discussion, which is your Q function sufficiently accurate? And we basically assume this regeneration, etc. So we get samples of every state action pair with a guarantee. And with 1,000 agents or even with 500 agents, it seems to be fairly good in this particular problem. So, but with 100 agents, it looks like we don't have sufficient representation. So your Q function is not accurate enough. So you don't have enough samples. And so it doesn't seem to converge to the true equilibrium. That's pretty much what I wanted to say. So if you will, our philosophy was find a computational algorithm, right, which provably converges to the Nash equilibrium, turn that computation algorithm into two variants of learning. The most obvious variant is just simulate the computational algorithm by virtue of a simulator so as to find the best response function. The other one was, rather than doing a simulator, use the world as a simulator. And so instead of getting samples with time, get samples with agents. And again, this question was, and we can show convergence in the same manner. I'll stop here. Thank you so much for your time.
So actually, let Sue he's the discussant, so let him take over and then I'll open it up for broader questions. Yeah. If you just stop sharing, then I think he can.
Yeah, I'm trying to locate the Zoom bar. There we are. Cool. Oh, wow. Okay.
Okay, go ahead, Sue.
What happened to it?
Okay, can you all hear me?
Yeah.
Yeah.
Yeah, so I'll just briefly overview this work. So the Trembling-hand-perfection is basically to restrict the strategy where agents sometimes can play unintended actions, and this perfection mainly could roll out unstable equilibria under some game perturbation. For example, it will rule out the equilibria where players play purely weakly dominated strategies. So for mean field games, the Trembling-hand-perfection consists of a tuple of strategy mu and the mean field distribution z, where given a z, this mu is optimal given this distribution, and using this strategy mu, this z is consistent with this mu. And so common Q value iteration can only converge to deterministic strategies, whereas this mu is basically 100% mixed. So they propose a TQ value iteration for to compute the Q value function for this Trembling-hand-perfection. Yeah. And yeah, the second concept is mean field games with strategic complementarities. So for strategic complements, the agents basically mutually reinforce one another. So which means that an increase of one agent's actions will increase the marginal utility of other agents. Of course, this is for just common games, but for mean field games, it will further requires like the non-decreasing supermodular conditions in both states, not all the states, action, and distributions. So basically, for this work, this monotonicity is introduced to ensure the existence of optimality. Here, this concept actually introduced a key assumption, which is that the state space and action space need to be totally ordered for these strategy complementarities to be well defined. And so they propose two methods to compute the equilibria. First one is model-based, and the second one is model-free. So for the model-based, which is the Trembling best response algorithm, they iteratively compute the Q value, the strategy, and the distribution. So to compute the Q value, basically they use the TQ value iteration, and then given this optimal Q, we can find the optimal trembling hand strategy with respect to this Q. So all these are given the mean field distribution Z. So the first two parts is from given this Z, we find the optimal mu. And then given the strategy mu, we can use the one-step of MV equation to compute Z. So the model-based method is straightforward. For model-free method, there are two places in the model-based method that actually use the transition function. So for the model-free method, the transition is unknown. And then, so when we learn the optimal Q value, we basically just use temporal difference learning. And for the mu, it's the same. And for Z, we can use, we can estimate the distribution using the next mean field algorithm they propose with samples generated from a simulator. But they actually also propose an online version which relaxes the need of this simulator by looking at the by storing a buffer of the state's evolution, and they can eliminate the need of this simulator by using the samples in the buffer. So I'm not that familiar with this area, so I just have a few questions. So first one is how this algorithm perform in practice in MFG without strategic complementarities, because I feel this is some certain restriction to the mean field gain we are considering. Second question is how does the trembling hand exploration epsilon affect the convergence? I mean, does it affect at all for the convergence rate, both theoretically and practically? And third question is the paper said that for the model-free method, they still assume that the reward function is known. But I think in not mean field gain, in usual reinforcement learning literature, not for mean field gain, like for usual MDP, the reward function is actually unknown. I mean, the R of SA is unknown, but at each, when we play each action at certain state, we will get that sample of R. So I feel that this work can actually sort of trivially extend to that case. Fourth question, so any challenges if the learning is decentralized, because in the learning algorithm of so there are T-MFQ learning algorithm, I think it's still from a view like there's an aggregator who knows all the state and actions, and so that the learning could be done. And the fifth question, I guess, just some random thoughts, how could be possible so that we could do any extension to partially observe mean field gains, like for example, there's a certain structure where so in this paper, the states is actually a tuple of states for each agent. So what if the agents can only observe their own states, but not other states? Yeah, that's my question. Thank you.
Cool. So let's answer these one at a time. So how do these algorithms perform in practice without strategic complementarities? The answer is surprisingly well. We don't know why, but effectively the algorithm that they used for computation, which is compute the best response, then take a one-step or multi-step McKean-Vlasov update, has typically done, I mean, so we've written many papers on mean field equilibria before, and we need to do our simulations and compute mean field and look at the structure and things like that. We've been using this computation algorithm for several works, many of which do not for sure have strategic complementarity. So, so the answer is it seems to do well in many cases. Now, the question is why, right? And we don't know, right? The strategic complementarities gives the specific monotone sequence of these mean fields, which converges nicely. But even without it, it seems to do well quite often. So at least in essentially all the papers I've written in the past, we use some variant of. We didn't do the learning part typically because we were just interested in computing it, but it seems to work. And I don't see there's a big difference between the computation part and the learning part, right? So answer is, yeah, it does pretty well in general. Does epsilon affect the convergence rate at all theoretically? No, it doesn't. You need an epsilon. Well, theoretically, it shows up somewhere in it. Practically, so this epsilon is basically giving you the amount you sample the other actions. It's the epsilon randomness in your sampling. Practically, it is required because otherwise you don't have exploration. But it seems feasible that you could decrease it with time. Now, the thought process behind leaving it fixed is, unlike a traditional, say, epsilon greedy kind of approach where the system is stationary and you're learning about that one stationary system, here the system is actually not stationary. It changes because every time you change the policy, everybody's policy has changed, so the system itself has changed. So you would think that you need a whole new exploration to deal with it. However, as the mean field converges, it is very possible that you could decay the epsilon. Of course, the nature of what is an epsilon greedy and, what is a Trembling-hand-perfection in this case with changing epsilons and things like that we'd have to think about. But I think it is feasible to decay it as time progresses. Next one, unknown reward function, as he pointed out, it's not a big extension. I mean, it looks like, I mean, you can do Q value iteration or TD learning or something with the unknown reward function. I don't see a big issue because it's almost like a black box there. You plug it in to obtain the best response, right? Any challenges if learning is decentralized? That's a good point. And I kind of alluded to it when I said, you know, this buffer is effectively all the samples are sent to a platform which is doing the learning. Now, there is work, for example, from Bashar's group on consensus, which has to do with the idea that you don't have such a platform. And so the information that needs to be shared is shared via communication, and how much needs to be communicated. Can you kind of, you know, share enough in a consensus manner such that you have enough to compute your best response and so on? That might be an option, right? So in other words, if you have all these agents who obtain samples and somehow you have an algorithm which shares enough of the mean field and the reward such that you can do your own TD at each agent, that might be appropriate. Of course, there will be another question of accuracy, how many agents you need, how much communication you need, but it's conceptually feasible. Extension to partially observed MFG. Now, agents in our MFG only do observe their own states. They don't observe anything else. They're given the policy by the platform. They observe only their own state, and they take an action. And of course, the platform gets back everything. They
do know the mean field though, right? Yeah.
They know the mean field, exactly. But
if the mean field is only partial, I mean, if you knew it with some error, what happens?
So with some error should be again possible, I think, because so if you look at the approach we have taken, that best response is a noisy best response. Noisy meaning to say it's not the perfect best response. It's run to a desired level of accuracy. So, but you do need some level of accuracy to get a certain sample complexity bound. In other words, the more accurate it is, the less it will take to converge, etc., etc. So I think there's going to be a trade-off there in that based on the how accurately, if you think about it, so in Vijay's question, we are actually only partially observing it in our final online algorithm because we have a certain number of agents, and that number of agents are the ones who are adding their data to the buffer. So how many agents there are is proportional to the, in some sense, the accuracy of the mean field. So the more you have, the better it is. So if you will, as you cut down the number of agents, you will get noisier and noisier mean field. And at some point, I mean, at some point you will be so noisy that your best response will no longer make sense. Kind of like, again, I guess if I could share this screen again, this diagram kind of answers the question here, right? This is a case where you have fewer and fewer agents in the system. This is, if you will, a noisy mean field, and these are less noisy mean fields, right? So at least empirically.
I'm going to ask a question on that. Do you have a sense of how many agents you need? I mean, so you could just,
it depends on the problem. So we don't. I know, for example, Lei has nice results on convergence rates and so on. Maybe it's feasible to think about, you know, basically number of agents versus accuracy of the best response versus accuracy of the mean field distribution. But yeah, it would need some work for sure.
I had another question on the sample complexity. I mean, that's for that particular algorithm. In this context, is there a lower bound? Do you know?
I don't think we didn't get one. We were thinking about whether, we finally didn't present it. We were working on a lower bound. It didn't show up in this paper. Kiyeob is here. Kiyeob, any thoughts on the lower bound?
I think lower bound will mostly depend on the lower bound of the Q-learning algorithm. I think it's doable. Once we didn't explore that space much. So yeah, I think it's doable, yeah.
So we haven't done it. We had some discussion on this at the time, but finally we wanted to understand the complexity of the algorithm in question. And essentially we wanted to understand how
in some sense, your algorithm, as you're coming back to your bound, it depends on the cover time, right? So if it is, in some sense, if it's a worst case kernel, then you're going to get the cover time be SA, right? Yeah, some SA is maybe S squared A or
it could be even larger.
Yeah, and so in that sense, it's fairly high complexity. Even in the worst case complexity sense, it will be pretty. We have an instance bound. An instance bound may be good for certain instances, but
yeah. The thing is, I mean, I guess the examples we considered were all pretty well connected Markov chains. So it did really well, right? We tried several examples and it converged pretty quickly in all of them. So, but it wasn't like long chains where you have, large cover.
Yeah, I mean, cover time and mixing time are sort of related. So, I mean, yeah, it's basically the worst, a bad type thing will give you problematic things. Any other questions from anyone? Sorry, I shouldn't be done. Lay or anyone else? Yeah.
So, yeah, I guess the question is coming back to Lay's question of is the epsilon randomness sufficient to provide a guarantee that you will sample all state action pairs? I don't see it. I understand that it's a finite state space, but it is possible that with time, occupancy in some of the states will just die out.
No, I mean, you'll have to make an assumption on the transition kernel involved, right? So it has to basically allow all policies will allow you to go everywhere. And if it's not, that's typically the way you would, in the literature, this would be addressed. This identifiability literature, but
yeah, also, sorry if I may.
No, go ahead.
Yeah, basic condition for Q-learning to converge is you need this property, right? You need to able to visit every state action pair. So even the policy, if the policy does not have that property, like even in one iteration, you cannot solve that problem.
I see.
So I mean, the model itself, if the model is known, has to have this property.
I see. But I see. So
transition kernel, if the transition kernel is bad, then you may have issues, right? Otherwise, I think the epsilon thing should work well, fine. Yeah.
I see. But Lay is pointing out that in Q-learning itself, that is kind of the assumption. Otherwise, how will epsilon greedy work in the first place, right? Because if the kernel forces you into some smaller subset of the state space, you will never get samples thereafter.
No, that's what I'm saying. You can have bad kernels, but if the kernel has some minimal property saying it is, then it will be fine. Yeah.
Yes, it would. You're right.
Yeah.
In
Also,
which case, we wouldn't need this regeneration thing.
Yeah, you wouldn't need the sampling. You can do it with the epsilon.
We can just do it with the epsilon itself.
Yeah, but you may not be able to do it one round. You need to have some mixing time to make sure it mix close to the steady state. So if you start from some bad state in one step, you may not be able to visit all the states.
Exactly.
Steps, right?
So yes, we obviate that by making sure you're well represented due to in fact, the proof only uses the regenerating agents. In other words, there are agents who essentially a certain fraction of them gamma will regenerate, and those are sufficient to do your Q-learning for you, which if you think about it is a very bad bound because really most of the agents would not have regenerated, all their samples are there as well. But as far as the proof is concerned, we only take the regenerating agents only, right, to provide your samples.
So I have another question. In your sample complexity, does you include the samples from simulation as well, or only the sample in terms of the real world iterations?
This was, I think, only samples from, let me just check. Kiyeob, do you remember what is the nature of the sample complexity bound again?
You mean the exact expression for the sample complexity? It was on your slide. We provide sample complexity for both model-based and model-free, right?
Do you count the data from simulation as a sample or it's free?
I think it's free. I think we're just looking at the number of times number of times.
That is the number of times we sample for the model.
In the simulator in this case.
Okay.
This is model free, and we also provide the sample complexity for the model based.
I didn't talk about model based at all in this. I mean, I guess Stu mentioned it in his summary. We didn't even talk about it in this thing. We just dealt with the one algorithm on model free. But yes, there is a model based variant as well.
Yeah. Also, there's some debate whether assuming a simulator is model based or model free.
Exactly.
Well,
I just want to phrase it.
No, model based, there is an actual formal definition, right? Model based versus model free is the space complexity. If the space complexity is little o of S squared A, little o of S squared A, then it is model free. Otherwise, it's model based. So basically, model based is effectively like constructing the transition kernel and then running it.
Right. Why?
But if you have a simulator, isn't that since you are querying every state action pair?
No, but you don't still, if you're doing the Q function, you don't need to actually construct the whole thing. The space complexity will be little o of S squared A. And
But
so that's
constructing the simulator.
So that's how Littman and everyone define it, right? I mean, there's a formal definition of model free versus model based.
I see. So in this context, is our usage of a simulator model based or model free?
Because you're using a Q function type thing, that would be a model free thing.
That is our thought.
You want to look at the space complexity, how much is used, because right. So you don't. I mean, even though you're collecting samples for the next state, you don't really form the transition kernel. You're just iterating with.
Yes, we are only iterating with samples obtained. So
your space complexity will still be little o of S squared.
What do you mean by space complexity?
Yeah, what do you mean by space complexity?
So for example, you could do the following, right? You collect all your samples and I form the transition kernel, right? And then I basically run whatever using that empirical transition kernel.
Correct.
Now that will be an algorithm which is sort of sample model based. Because now what is the size of what I want to get that transition kernel. So I need it, it'll be roughly on the order of S squared A. Right? When I don't do that, if I implement it differently, then I could get basically, say a number of samples I'm taking to construct, then the Q value, it doesn't increase linearly with S, with sublinear in S. Then I have little o of S squared A space complexity.
I see. That is
the Q learning require S times A, I think, at least.
No, S times A is fine. It's S squared A.
Oh, S squared. Okay.
Space complexity part, right?
Okay. So basically, you're saying how many samples do you need for your algorithm to do what it does, right? In model based, you're saying it's like S squared A. In model free, it's like O S squared A, like S.
Yeah, it's like the space complexity, what you use, what type of structure you build up, and then you use to run the thing. And that's the distinction they use. At least this is Littman and Kakade and all. The usual guys.
Kiyeob, then in our sample complexity, we did the model-based version, which is essentially building the empirical transition kernel and doing.
Yeah, so that would be that will be big O of S squared A.
I see.
Little o of S squared A.
I see. We'll have to check how the essay came into that. Yeah.
So any other questions? If not, let's thank Srinivas again.
Great. Thank you for coming. And I guess we can quit.
All right. See you. And then the video will be up sometime tomorrow on YouTube channel. All right. Okay. Bye.
Bye. Nice to see you.